Today, I'd like to welcome Dr. Malcolm Ross to our DeepPower podcast. Malcolm is currently a strategic advisor at Ever Technologies and teaches Introduction to Geothermal Energy at the University of Texas at Austin and is an adjunct faculty and lecturer at Rice University. Prior to his time at Rice, he was a research scientist at Shell International and a black swan detector for Shell. Prior to Shell, he was CTO of Landworks GSI, director of Central Region Operations for GIS Technology, and director of PaleoMap Foundation. Malcolm, welcome to today's podcast.
Hello, thank you. Yep, glad to be here.
It's a pleasure to have you. I love on your LinkedIn profile, you call yourself a geothermal evangelist. I'd love to hear from you. What does that mean, and what opportunities have you had with that kind of title?
Yeah, so there's a real sort of story behind that. That's a good starting question. The role is about trying to lift all boats for geothermal. I selected some years ago geothermal as where I wanted to put my heart and time and effort, money, and I wanted to be successful. So I decided to try and get into a place where I can do things that lift it up in the marketplace. And so that's really what I do. I try not to get behind any particular company. You mentioned I'm a strategic advisor to Ever. I'm a strategic advisor to 4 or 5 other companies as well. So it's not like I picked one company or technology. I'm trying to raise all boats is the way I think about it. And I chose that name really for a specific reason. You mentioned Black Swan detector. Before that, my title was Game Changer. And what I learned when I joined the Shell Game Changer team, which is halfway through my Shell career, was that, and I should say, Shell Game Changer is a entity within Shell that does angel investing. We looked for ideas on the back of the cocktail napkin and selected a rare few and gave them funding to try to get them to an investable stage. And we didn't ask for equity. We asked for commercial rights, assuming whatever they did finally went commercial, then that's what that would be our reward. What I learned when I had a business card that said my title was Game Changer and I'd hand it to someone, it would start a conversation. This conversation, that's what I just explained. And that would generate, oh, I've got an idea, and off we would go. Right. So when I left that team after 5 years, because at Shell, that's what we do. We just rotate through jobs. I went to another team. There was a new energies research team at Shell, and we were supporting the new energies business. And the new energies business had been spun up as a standalone entity within Shell. It's now been reabsorbed, but it was standalone for a while. And we were responsible for providing the R&D to support that. And what I noted was that they had selected wind, solar, batteries, biofuels, hydrogen as the things that they wanted to do, to the exclusion of geothermal, nuclear, ocean energy. There's a bunch of other technologies that they had strategically chosen not to spend time and money on. And I said, that's creating blind spots for you. And innovation, like the innovations that we were encouraging over there in Shell Game Changer, could change the economics for any of these things you chose to ignore, and you could get blindsided. And so they said, oh, great, then that'll be your job. And I said, fine. That's why I gave the presentation. I wanted to sit outside the box. And so that was my role, that's where the Black Swan detector came from, was that I was looking for changes to those things that were outside of the box that suddenly made them more interesting. Wow. And I chose Black Swan because, number one, it was remarkable. People would remember it. And guess what? It would start a conversation. Business card says Black Swan. What is that? They get the same message I just gave you. And then I also liked it because the acronym, BS detector.
Because together, yeah.
Yeah, that's part of the job, is it? Detecting what's BS and what's not.
Right.
So, the lesson learned there for me was this idea of having a memory tag associated with you and what you do, and it starts conversations, and that's key. And it's about these relationships, building the relationship. It's like a really good pickup line at a bar, I guess. Probably. It's a way to think about it. So when I left Shell, there's a whole story behind why that was. I realized that I needed another title that people would say, oh, that's interesting. Tell me about that. Like what you just did at the beginning of this conversation. And I came up with geothermal evangelist because A, it described what I did accurately, but B, it makes people like you and the audience interested in who I am and what I do. And when somebody says evangelism, oh, they'll think Malcolm. That's the whole that's the story. So there's in a nutshell a little bit about my career and then how I sort of found this that included remarkable, memorable kinds of titles.
I love that. Well, in a previous conversation, we had talked about how you actually had a dual major in theater and in the sciences. And I'd love to hear a little bit more, but I can tell just from your theater background, perhaps that's what allowed you to think differently strategically, how to present yourself in a way that'd be attention grabbing. I could see how those things may have blended together because, it's not always normal that the right side of the brain and the left side can end up working together. So, tell me about your background theater and then the sciences. And then I'd love to hear how that kind of helped you become a professor at both UT and Rice.
Sure. So I started theater in high school musical, the whole nine yards. And then when I went to Colgate for my undergraduate degree, I did a double. They called them concentrations back in those days. And when I graduated, I had enough credits in both departments to receive that concentration award. And so I had to choose if I was going on to graduate school, whether to do a master's of fine arts or a master's in in science. And I chose the science side because I figured that's where the jobs were, and they were always unemployed actors. And so I went to University of Texas and got a master's. And when I graduated, there were more unemployed geologists than there were unemployed actors.
Oh, no.
It was a downturn in the industry, and how's the joke go in Texas? How do you get the attention of a good geologist? Hey, waiter, that's a spin on the old joke of how do you get the attention of an actor.
Yeah.
So I went on to get a PhD at Rice University, and because partly in waiting for the jobs to return. And I finished the PhD and I'd gone through a full economic cycle in the oil patch. And by the time I graduated from PhD, another downturn in the industry. So I didn't get a job. I actually did several startups. We didn't call them startups back then, but they were startups. And I did that for about a decade. And then I went into GIS. So you mentioned these companies, Landworks and GSI and so on. I got out of geology entirely because of the downturn. And I focused on GIS technologies, digital mapping. And my big customers cared about where were the wires and transformers and gas pipelines. It was nothing to do with geology. And then I got back into it when the oil price came back up. So the theater aspect of that is that I am pretty well known as a good public speaker. So I was, I think, successful in the sciences because of my public speaking, engaging, fun to listen to, and well thought out. So I would say that plays into it. And then, and so with defending a thesis or whatever, I was pretty effective at that. I also did community theater while here. That sort of fed my acting Jones, as they say. And then I discovered that at Rice University, they didn't teach GIS technology at all to the students. And I felt it was a crucial skill, not just for the geoscience students, but for engineering, social sciences, all these people who use digital maps in various ways. And so for a decade or more, I taught GIS technologies at Rice. And it was really focused on how to use it in what you do, not here's a theory of map projections and blah, blah, blah. It's let's apply the technology effectively in whatever you do. And I got social scientists and engineers and all sorts of students in those classes. And it's only last year that I decided to set that aside and get into doing geothermal, teaching geothermal, because I'm trying to feed the human employment chain of geothermal. But what I learned was teaching is just another form of acting.
Mm.
It's improv. It's really trying to react and be entertaining, because we've all had professors who just droned on reading from their notes. I'm not one of those guys. Okay.
Oh, I can tell.
And I think that's what makes me an effective professor, I think. And that's why that's where I get my acting Jones these days. And oh, by the way, video podcasts.
Oh, good. Yeah. Well, it's
although you're my first, and I hope the first of many.
Oh, good. Well, it's interesting. In my freshman year in college, I needed an elective to take, and I took a geology class. And I think I could have loved it a lot more had my professor been more like you, because he was as boring as a rock. And I think with your personality and background, it can make all the difference in the interest of a young student trying to figure out what they want to do with their life. I mean, the enthusiasm that you share and how you make it fun, I bet. So it would have been fun to be a student in your class. Unfortunately, that didn't happen, but maybe, we came full circle. Now we're meeting together. And
and for me, the way I measure success, and I saw it in the GIS class, when students picked that as a career. They didn't come in the class to set it as a career. They came in as engineers, social scientists, geologists, whatever, but they chose a career in it. And often as an instructor, as a professor, you don't hear about that. But when you connect to them on LinkedIn along the way, then all of a sudden you see that they've got a career taking off in the in GIS. It's like, okay, that's success. And then for this GIS class, for the geothermal class, I've had about a third of my students so far, and just teaching it twice now, a third of the students accept jobs or internships in the geothermal industry. Essentially the same thing is happening, redirecting their career.
Wow.
And that to me is how you measure success in
Congratulations.
teaching.
Yeah, that's wonderful. Yeah. It's interesting. I was on the University of Oklahoma campus a couple of weeks ago talking to some professors about the life cycle of geothermal, and kind of, it's been around for obviously thousands of years, people being able to find natural hot springs to heat things. But this professor had mentioned how, fracking in the oil industry really has only been around for a decade, and the advancement of that technology, whether, it's controversial and everything, but his point was that fracking really wasn't known or widely accepted a decade ago. And within 10 years, it had totally changed the oil industry. I think similar, conversation about geothermal 10 years ago, while you were at Shell, even though you may have been looking at geothermal, I mean, I'm curious, it was nothing like it's at today, right? There was other energy sources that were being far more adopted or researched. Now, I'm curious, from where you were at Shell looking into these new exciting technologies to today, where have you seen geothermal kind of progress in that time period?
Okay, yeah. So I started with Shell in doing geothermal in the Game Changer team. Yeah. So some of the technologies that came to me that were geothermal related, in particular, technology from Green Fire Energy and from Ever. And so I was in the oil and gas side of Game Changer. So we were looking for disruptive technology on the back of the cocktail napkin in oil and gas. And the other half of my team was looking for new energy disruptions. And I wanted to be on that side because I've always felt honestly guilty about working in the oil patch and being part of the machine that creates carbon in the atmosphere. As a paleoclimatologist, I sort of had an appreciation for that, deep appreciation for that. And so I was looking for a way to get out of the oil and gas space. And so in Game Changer, as these ideas came to me, I said, that's my route out of fossil fuels and all of that. So I went into Game Changer. I went into the geothermal from there. So I felt that for geothermal, the breakthrough technology was closed loop geothermal, not EGS. EGS has been studied and around for quite a time now. A lot of efforts being put into progressing it. The Forge site in Utah is making some spectacular breakthroughs. Great for them. A lot of good people working on it. But for me, the opportunity where I wanted to put my effort was closed loop, because, as you say, fracking has its associated problems and is maybe not going to be effective in, for example, Europe or in parts of the Northeast or California. etc. So I was looking for something that was more widely distributed. In fact, at Shell, one of the things I ran into was that Shell had deliberately chosen not to pursue geothermal in their new energy business because of the limited geographic extent. They had calculated that 9% of the earth was going to be suitable for geothermal. And we should clarify, they were thinking traditional, even EGS-based geothermal was too geographically restricted. And so to me, the breakthrough was closed loops and geothermal anywhere could spread to 80 or 90% of the earth, and then that should make geothermal interesting. So for me, I think the breakthrough that's going to lift the industry and bring all the other technologies along with it is closed loops. And that's why I chose to be a strategic advisor to Ever, among others, on closed loop technology. I think the shale revolution and fracking is important, and will make EGS a viable opportunity. But even more important, I believe, is the advancements in drilling technology.
Yeah.
Because the drilling technology applies to everywhere in geothermal.
Right.
The rate at which we drill has gone up remarkably, especially Forage is breaking records every time they drill now with a variety of approaches that are really improving the drilling rates for geothermal in hard rock. And so when I originally did the work at Shell on geothermal, they asked me to find out why Shell wasn't in geothermal. So I went out and interviewed a bunch of people at Shell. I interviewed experts outside of Shell, and I came up with a top 10 reasons why not. And it was sort of a David Letterman kind of list, and the number one reason, actually the top three reasons were cost of drilling and casing, cost of drilling and casing, cost of drilling and casing.
Yeah.
The point is, if you can't solve that problem, you might as well not solve the other 9 problems.
Right.
And so I think the shale revolution, biggest impact in geothermal will be in the drilling, not in the fracking side of it.
Yeah, that makes sense. There are some critics though on closed loop saying that, other research shows that might not be a viable option as opposed to EGS. I'm curious, from all of your background, how would you kind of approach the critics and from what you know about Ever technology and other closed loop options, what would you say to that? People saying that it wouldn't be viable, that it would just be too hard to connect them, two different drill, well bores. How would you kind of defend the closed loop section of geothermal?
Right. I think the primary criticism of closed loop, and it was true at Shell when I began to adopt it, is the reliance on pure conduction as a way to transfer heat to the wellbore. If you can get convection going, then you have a much more rapid way of exchanging the heat. And when you remove heat, new heat can come back to replace the heat that you've done. With conduction, once it's gone, it's gone. It becomes a limited resource in some sense. And so that's been an issue. And so I think various companies take various approaches. You ask specifically about Ever, so I'll speak to that. Ever's approach is the multilaterals, to basically expose yourself to a greater volume of rock by drilling down vertically and then branching out like the tines of a fork. And the idea is to drill down vertically as fast as you can, relatively large bore, get to the right formation that has the right characteristics and it's the hottest thing you can find, and then go either not necessarily horizontal, maybe 45 degrees with the tines of your fork. That's essentially drilling what you would normally think of as what you would frack. You frack in order to get in, heat from a larger volume of rock. This is drilling that instead of fracking that. Yeah. And so that's their approach to the conduction problem. Now that introduces a new set of problems. That is the cost. Back to the cost of drilling. If you're drilling multilaterals, how are you going to avoid all that drilling cost? Yep. And the answer is only half of the cost is drilling. The other half is casing, cementing and casing. So Ever's approach is to not case and cement the tines of the fork. What they choose to do is, number one, the target formation is as least porous and permeable as they can possibly find. You're trying to find the least porosity, not the most, which is normal, what you normally try to do. And what they do in the drilling mud is introduce a polymer that is pH sensitive, that any kind of porosity permeability that they might encounter with a mud, the pH drops and the polymer solidifies. So essentially you're casing with plastic while drilling, sealing off the formation. So that is one way to get around the drilling and casing costs is reduce the cost of casing by not casing. And then the forge-like drilling and all of that is decreasing the cost per meter of drilling. So that helps. And then the question you mentioned about connecting them. So when Ever was doing their first pilot project, they called Everlight, Shell was helping me through Shell, was helping to fund it. And we set them 3 goals. One is to make these connections. 2 was to seal the pipes, which I just talked about. And 3 was the conduction problem, the thermodynamics problem. So at Everlight, they were able to drill vertically. I think they were something like 3 or 4 kilometers apart, go horizontal and meet 8-inch holes at 2.5 kilometers end to end. They backed up, deviated, and did it again. And to us, that proved that the meeting of the wells isn't the problem. They use magnetic ranging to do this, and magnetic ranging is used normally in oil and gas if you have a blowout, like the Macondo blowout, and you want to intersect that well bore from a relief well, you've got to find that well bore. Well, magnetic ranging is how you do that. So this is not a new technology. They're just using it in a slightly different way. The polymer, by the way, is also used normally in drilling to seal circulation problems. So if you drill through a crack and that crack starts to cause your mud to leak out of your well, they introduce this same polymer, more or less.
Yeah.
And so none of this is really actually new technology. And so finally, that third element that we demanded of them was to do a thermodynamic model in advance. And then, and that thermodynamic model showed that the conduction problem was not the problem people thought it was. In fact, that the temperatures do not precipitously drop off. They actually flatten out and become relatively constant. And we made sure that they'd done their modeling in advance. And then we said, okay, now for that location, what is your modeling? Does your modeling fit the real world data? And the answer is it fit within 4%. And so their thermodynamic modeling, 3-dimensional modeling that people weren't really considering all the factors. And it's kind of a deep technical discussion as to why conduction really isn't the problem that people say it is. But in any case, they were able to show us at Everlight that the 3 biggest challenges were not the challenges that people thought they were. That didn't convince Shell to go into geothermal, by the way, in any kind of way. But that was exactly the questions that you were asking. We're being asked 9 years ago when we first started down this road.
Right. Well, I appreciate that background because I've had people ask me the difference between EGS and closed loop, and I haven't educated myself enough. And that what you say is interesting and makes sense. And you had mentioned just the challenges of drilling, and I can't agree more that the traditional oil and gas industry hasn't needed to drill deeper than a couple kilometers, right? There's no more oil down there, or it's not cost efficient. One of the things at DeepPower, one of our technologies we're researching at the University of Oklahoma, is a new and novel way to drill. And we're encouraged because just our initial lab results show a 600% increase in drilling rate penetration over traditional oil and gas. And
can you talk about that? Is it lasers, microwaves?
So it's not. It's a novel mechanical way to drill that hasn't been tried before. And what's interesting is we compared that against the Quaise type plasma pulse. Well, it's not plasma. Excuse me. The millimeter wave type drilling, and our data compared to their data shows a 300% increase over rate of penetration on their millimeter wave. So we're very encouraged. We just launched a new drilling rig at the University of. It's a test drilling rig, but we're on to that phase.
The tallest rig in yeah.
Yeah, and people didn't understand that it was the tallest a university lab rig. Obviously, there's much taller real life rigs, but yeah. So you saw that article, which was great, and we're really excited. Once we get through this next feasibility, this techno-economic feasibility study, we call it, to see, okay, if we can drill faster, that's great, but how much more will it cost, or how will it cost less? So once we get to that phase, there'll be some great results we can share. But I can't agree more. And even Shell's analysis of 9% of the Earth's geology can have geothermal available. Our goal is that if we can drill 6 miles deep anywhere on the Earth, you can reach the temperatures that can provide, sustainable,
geothermal anywhere.
Geothermal anywhere, but 6 miles is a very long way, and if drilling is the number one cost, and then obviously casing, if we can reduce that significantly, then that opens up the barriers around the world of being able to drill. So it's a very big project, and obviously there's a lot of hurdles, but that's what I like to do. I like to go big and see if we can to solve those. But I think that
the biggest element, another element of it, is temperature, right? It's not just depth, it's temperature, right? If you're talking about super hot rock, you're talking about 350, 400 centigrade, and electronics off the shelf drilling related to, they work up to 150 feet. So that's as much a limit, and for oil and gas drilling, they're never worried about 150 C and above, anyways, because those kinds of temperatures would destroy the hydrocarbons.
Oh yeah.
So they weren't really ever drilling. Some high pressure, high temperature drilling gets a little bit hotter, but really never to the kinds of temperatures we're looking for in geothermal. And it's a non-linear relationship between the temperature and how much energy you can get. So getting hotter, a little bit hotter, is a lot better. So I think that's crucial is to getting geothermal anywhere, and getting geothermal to have a big impact in the energy system is getting to these higher temperatures.
Absolutely. Well, you bring up a good point, though. I mean, the sensors, the electronics, even the drilling fluids, you can't frack, or your traditional muds, all of that can't withstand those temperatures. So you're very right. There's a lot of seals. Yeah, exactly. I mean, there's a lot of innovation that has to happen along the entire tech stack. And it's exciting to see, many different companies trying to innovate on that. But there is a lot of work that has to be done, and we're eyes wide open to that.
One of the wrinkles that Ever is doing, and I think is also being pursued at Forge, I think is really clever. And that is to, instead of changing the drilling technology, stick with the same PDC bits, mud, etc., but use an insulated drill pipe that allows the mud to get down to the bottom of the hole at a cooler temperature.
Oh, interesting.
So it doesn't absorb heat from the surrounding rock. And when it hits the bottom hole assembly, it keeps the bottom hole assembly cool. So they did an experiment called Ever Deep in New Mexico, where they kept the bottom hole temperature within the normal operating range of off-the-shelf equipment, while the rock was 300 C, I believe, is with the temperature. And the other effect of this, and this I think is interesting, the cold mud hitting the hot rock caused that rock to fail, thermal spallation. And so it softened the rock in front of the drill bit. And what they're seeing is an increase in the rate of penetration related to that. And the hotter you go, the greater the effect. And so you actually see an acceleration at the higher temperatures while using the same off-the-shelf technologies, which companies are comfortable with, familiar with, etc. So I think that's a sort of easy way to get us deeper and hotter. We still probably need gallium arsenide chips and metal connections, blah, 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 all that eventually, but especially if we're going to go to supercritical. But yeah, I think there's some clever things we can do to get us a lot of the way there here in the short term.
Yeah. Well, and I was talking to an oil and gas executive a couple of weeks ago, and they had mentioned how really geothermal is kind of like the Wild West, like akin to the gold rush times, where there's a lot of new startups that are trying to get into the industry, where usually your big Chevron, Shells would be the leaders. There isn't a big enough economic reward yet due to the cost, right? So that it's allowing for these smaller startups, even companies like DeepPower, to have a place that they normally wouldn't in other industries. And this Wild West gold rush feel, there's a lot of excitement, there's a lot of unknowns, a lot of people are trying to figure things out. The industry is still young, and it does give people an opportunity that might not normally have a chance in an industry such as big as the oil and gas industry. But one of the things that I'm curious to ask you about is, from your time at Shell, identifying these new startups, how have you seen geothermal and the opportunities that geothermal has in comparison to the things you had mentioned, solar, wind, the oceanic power? Like, why do you see geothermal, or and maybe you don't think it's better, but I'm just curious how you've seen the differences and why you've leaned more towards geothermal.
Yeah, I think there's a couple aspects of geothermal that really intrigue me, and I think are underappreciated. I would start with how you use the heat when you get it to the surface. One way is to make electricity, and that's the traditional way everyone thinks about it. And that's really a historical thing related to the fact that geothermal could only be found or be done only where you could find manifestations of it at or near the surface, hot springs and that kind of thing. And those were nowhere near the customer. And since heat is difficult to transport, they said, okay, we'll convert to electrons, put it out on the grid, and then we can use the transmission network to get our product out to the world. The problem with that is the conversion of heat to electricity is inefficient. Carnot's law and all of that. Even at temperatures, very high temperatures, the efficiencies are somewhere well below 50%, often well below 30 or 20%. And if you are then taking that electricity, putting it on the grid, and in the US, about half of the power usage goes to heating and cooling. So you're converting it back to heating and cooling at another inefficient process. And so it never was the best use of the heat to make electricity out of it, because once it's electrons, it can do one thing. It can do what electrons do. What is underappreciated, I think, is the direct use element of it. Why convert it? Why not, if you're going to use it to make heat, why not, once we get to geothermal anywhere, we can use the heat close, we don't need the transmission. We build a small geothermal plant in somebody's backyard or in the backyard of a factory and use the heat directly, and don't suffer the inefficiencies of converting and then converting back, etc. So I think that's a huge win for geothermal in a growth area. In fact, that's what's happening in Europe. Most of the geothermal now we're talking about for Germany and sort of Poland and the eastern part of Europe is heat directly into heat networks that go to heat homes and commercial buildings. But the other element of it is that the direct use can be cascaded. So the waste product of, let's say you make electricity, the waste product of electricity is perfectly good for beer brewing and distilling. And the output of the beer brewing and distilling is great for greenhouses. And the output of the greenhouse is great for something else. And so to me, there's a whole value chain there that when you don't need quite so much heat, or because the electricity demand is down, you can feed that further down the chain, and you can optimize the chain based upon your desires for profit or for CO2 reduction or whatever. You can emphasize different parts of the chain. With making electricity, you don't have that. You get electrons, you sell the electrons for X cents per kilowatt hour. That's it. And so I think there's a huge opportunity in the direct use space that is underappreciated, and was underappreciated because of the historical fact that geothermal was geographically limited. So we're back to that geographic limitation. If we can get to geothermal anywhere, then geothermal direct use becomes very, very attractive in my mind. So I would say that was one of the primary reasons that I got interested. And then, in fact, if you are looking for direct heat for homes and commercial businesses and industries, the temperatures that you need to get to aren't as high as you need for electricity. So geothermal anywhere isn't as hard as we think it is, which just, to me, a mindset change. And it's happened in Europe, and it's starting to happen in the US. I think one of the couple of great applications of this sort of direct use approach is data centers, which use a huge amount of electricity, sure, for spinning disks and running computers, but most of it goes to heating and cooling, mostly cooling. And absorption chillers can convert heat into cooling, a cool water stream, at about 75 to 80% efficiency relative to converting it to electricity and then using that electricity to run an air conditioner. And so you could put a geothermal location right next to a data center, provide all the heating and cooling and electricity right there, but within the fence for the data center, and providing it 24/7, reliable, resilient, all of that stuff that the data center is looking for. Another interesting one is direct air capture, so and CCUS. So you can use the geothermal energy to power a CCUS location. In particular, in direct air capture, there's a huge volume of air that has to move through the system in order to have enough capture 400, 500 parts per million of CO2. Takes a lot of energy, but so it's not green if you're using the grid to power the fans, right, that are pushing all that air. So if you use a green source like geothermal or wind or solar, then you get a much lower CO2 impact of the sequestration of the CO2. And the other element of it is that in direct air capture and a lot of capture technologies, you have a material that's absorbing the CO2, and it has to be regenerated. Once it's saturated in CO2, and then you go through a process to clean it up and take the CO2 out of it. What is that process? It's a heat-based process. So not only could you use the electricity from a geothermal plant to power the fans, you can use the heat to do the cleanup of the absorbent and recycling. And by the way, the CO2 that you create could be reinjected into the downgoing stream of water that you just, hot water that you produce to the surface and are using. You've got to reinject that somewhere. You could put the CO2 in that brine, and it could be part of the reinjection process. So again, like the data center, a self-sustaining green way to impact the CO2 sequestration world. So that's just a couple of sort of pathways. So with wind and solar, great, that's fine. Storage, you get your electrons, you sell your electrons. Boring, as far as I'm concerned. It sounds really, and I guess investors like boring, but for me, who's on the creative side and on the integration side and putting crazy things next to each other and seeing how they interact, that to me is the most exciting part of geothermal.
Well, thanks for sharing. I mean, you gave a lot of great examples of the applications and use of geothermal, which I think are very inventive and could be very useful. I think when people ask me, are we competing with wind and solar? And my answer is, they all have a use case that could be very applicable in certain scenario situations. And really what I try to tell people is there's got to be like a platform of alternative energy that can, sustain our planet and our populations. And our hope is, as we all know, geothermal is always on 24/7, but there still are valuable use cases for wind and solar. So we're not knocking those or saying, hey, don't ever use them. But we do understand that solar became so popular residentially, commercially, because there were huge incentives and tax breaks, right? Subsidies. And I think if we're going to really widely adopt geothermal, there's going to have to be some private public partnership where there are also incentives to reduce our grid requirement from coal or natural gas by going to geothermal, right? So that's a different conversation. I think lawmakers need to see that geothermal will work. It's sustainable. It's, somewhat cost effective. But I think, that's when they may need to start kicking in on subsidies or things to incentivize, that to go commercially. So, but I appreciate your examples, and I love your enthusiasm when you're talking about them. Again, I can only imagine what your students are thinking when you're sharing all of the the introduction to geothermal to them. So, Malcolm, I really have appreciated our time together. We haven't had enough time. We could keep going for hours, I'm sure, and maybe we'll have to invite you back again on round 2. But your expertise, your enthusiasm, is contagious. And one thing I just want to thank you for is someone has to be bringing up this next generation of thinkers and scientists that will solve some of the problems that we have. And I appreciate your efforts and excitement and the joy you have in watching your students succeed and get into the industry. And, who knows, maybe we'll end up hiring one of them, right?
I hope so. Contact me. I'll have a whole new crop coming up here after the fall.
That is awesome. Well, thank you so much. It's clear you're an expert. We want to keep relying upon you and other comments and things. It's like I said, we'll invite you back, but appreciate your time, and we'll be continuing to watch what you're doing with your career and your students, and we'll be able to stay connected together.
Thank you, Andrew. Appreciate it. I enjoyed the conversation, and I look forward to doing it some more.
Thank you, Malcolm. Have a great weekend.
Thank you.